This meeting is being recorded.
So does everybody hears me? Nobody hears me.
Yes.
Okay, very good. Because I'm sorry for the delay. I had connection problems. Okay, so welcome to today's seminar on non-associative algebras. So let me introduce today's speaker. It will be Saïd Benayadi, assistant professor of the University of Mass, whom I know since I think 30 years at least. And his main field of working is research is structures on say algebras of all kinds, Lie algebras and other, in particular invariant or scalar product type structures on which he has published, I would say, at least 50 papers. And we met ourselves when he actually found a counterexample for a conjecture I posed. This was back then in the 90s. And so today I have to see he is going to speak about again structures on non-associative algebras. I have to find, he will tell you in a minute. Sorry. I think, Said, the best thing is you present your title yourself, and I'll just let you talk and share the screen with your
Okay.
things. So thanks.
Thanks, merci. Merci. Okay. First, I thanks many thanks for Ivan for his invitation. This talk is about a class of pseudo-Euclidean left-symmetric algebra. Okay, I start in by presentation of this problem. We know that important links between differential geometry and non-associative algebra is achieved through the study of the geometry in general of homogeneous space or Lie groups in particular. This type of links has made it possible to consider the study that is the subject of this talk. Throughout this talk, G with the bracket with the non-degenerate bilinear form will be called pseudo-Euclidean Lie algebra, and we denote the bracket or the adjoint action by this notation. Okay. Now I can in some things in this subject. The Levi Civita product associated with this Lie algebra with this scalar product here. It's not, in general, it's not definite bilinear form. Is a unique product. On the underlying vector space G, such that the bracket of Lie algebra is defined by this product, and this product verify this. That means that Lx, the left multiplication minus the adjoint of Lx is minus Lnx. The Levi Civita product is unique as is defined by this. And this, here we remark that that this product is defined, completely defined by the scalar product and the bracket of Lie algebra. For notation, for any x in G, we denote by Lx or Rx respectively, the right multiplication by x, and the Lx is the left multiplication by x. If this scalar product is defined for positive, or signature n-1, we call G Euclidean in the case of defined positive, and Lorentzian if the signature is n-1, 1. The curvature of this pseudo-Euclidean Lie algebra is exactly this one, where Lx is the multiplication, the left multiplication by x, and G is called flat if this curvature vanish identically. And for notation, for endomorphism or linear map from G to G, we denote by F star its adjoint with respect this scalar product. First, recall that Euclidean Lie algebra is called flat if its curvature vanishes. This is exactly this definition. It's the repetition here. This means that the Andean vector space of Lie algebra G is endowed with the Levi Civita product is or left symmetric algebra. In this case, you have vector space here with the bracket. In this case, we have Lie algebra, but if we consider the same vector space with the new product Levi Civita product, in this case, you have we obtain a left symmetric algebra if the curvature is zero. If this one, okay. Now, recall other definition. If you consider a non-associative algebra A, this algebra is called left symmetric if your associator is here. The definition of associator is here. If you have this identity, okay, this identity, this non-associative algebra is called left symmetric algebra or Pauli algebra or Weinberg algebra. If this non-associative algebra verify this, that means that Lx and Ly commute. In this case, we say that we have L algebra, R algebra if we have this commutation of Rx, Ry, and Rz. LR algebra if it is at the same time L and R algebra. Novikov algebra if it is at the same time left symmetric and right algebra or R algebra. Okay, this we're now in definition in non-associative algebra. Now let us recall that left pseudo-Riemannian metric on Lie groups is called flat if its curvature vanish. And in this case, we can the Lie algebra of these Lie groups with this bilinear form is a pseudo-Euclidean algebra. And when this if this pseudo-Riemannian group is flat, in this case, it's equivalent to have its Lie algebra pseudo-Euclidean and flat. And in this case, in the underlying vector space of G, we have left symmetric structure defined by Levi Civita product. Consequently, the studying flat pseudo-Euclidean Lie algebra is equivalent to studying pseudo-Euclidean left symmetric algebra with symmetric non-degenerate bilinear form, such that left multiplication in this left symmetric algebra is skew-symmetric with respect this product. Now we can study this family or this class of non-associative algebra. Okay, donc it is well known that left symmetric algebra are an important class of non-associative algebra, which appear in many areas of mathematics. In the literature, very few classes of flat pseudo-Euclidean Lie algebra have been studied. It's the study of all this Lie algebra is it's very difficult, I think. The first class is the case where the flat left invariant metric is a Riemannian. In the first class, this class is completely classified by John Milnor in this paper. Okay, in this paper, I showed that in the Euclidean case, an Euclidean Lie algebra is flat. It's flat if and only if this Lie algebra is. We can decompose this Lie algebra as a direct sum of Lie subalgebra, but abelian subalgebra, and an abelian ideal. And in addition, add x is just is the adjoint action is skew-symmetric with respect to this one, but for any x in this Lie subalgebra. Okay. In general, it's not. It's almost quadratic, but it is not the case. Just add x for x in B as skew-symmetric with respect to this. This result of Milnor classify the Euclidean Lie algebra. The Euclidean Lie algebra, but the problem in the non-definite case, it's very interesting, but interesting, but very difficult to classify. It's not easy to have a classification for all non-Euclidean Lie algebra, but we can give some description of this of this type of algebra in the Lorentzian case. For this, Anne Ober and Alberto Medina introduce a processes of double extension to in order to give some information in the case of Lorentzian case. I recall this double extension to have some idea of this technique. We start by the flat pseudo-Euclidean Lie algebra, and we consider two endomorphisms C and D, two endomorphisms of B, and one element in P and a scalar in R, such that Xi is one cocycle of this with respect to representation L, not adjoint representation, but the representation defined by this one, because in this case we have this Lie algebra is flat, and you have this. The curvature is 0, is equivalent to this. Okay, and this means that this linear map is a representation, and Xi is one cocycle of this representation. That means the Xi bracket AB is equal to this. This one is exactly one cocycle of B, but not with respect to adjoint representation, but with respect to this new representation given by the Levi Civita product on P. The second condition, this endomorphism is skew-symmetric with respect to this one, and we have this condition. And for any, we need this one. Okay. If we have this condition, Medina and Ober call this data by admissible data. Okay. If you have this, if we have this condition, we can consider this vector space is the dimension of G is the dimension of B plus 2 with the inner product defined by this, which extends the first one in B, for which this vector space, so subvector space, and B are orthogonal. That means this one and this one. And in this new vector space, we define the following product. The following product, and two element of B, we have this, and this one is exactly the central extension of this one. In this one, pardon. This one is a central extension. Is a central extension of B, and the scalar cocycle is here to make this. And the other one here is another extension of this this Lie algebra by one-dimensional Lie algebra. It's just direct sum, semi-direct product, and we have two extensions to construct this new Lie algebra. For this reason, we call this type of algebra double extension. We have the first extension is central, and the second is semi-direct product or generalized in general, generalized semi-direct product, pardon. And this new Lie algebra is also flat pseudo-Euclidean Lie algebra, and is called flat double extension of this. And double extension because we have two extension. This is the double extension by one dimensional. It's the double extension of this one by one dimensional Lie algebra. Conversely, if we consider a flat pseudo-Euclidean Lie algebra which admit one dimensional isotropic two-sided ideal such that its orthogonal is also two-sided ideal, in this case we obtain G is obtained by this process. Okay, donc the problem in this type of description, we must found this type of ideal, isotropic ideal, one dimensional derivative, such that its orthogonal is two-sided ideal also. In this case, you can say that there exists an B flat Lie algebra of dimension of G minus 2 here, and you can construct G by this double extension. This is the result of the process of double extension by one dimensional Lie algebra introduced by Ober and Medina. But the classification of flat pseudo-Euclidean Lie algebra seems very difficult. But nevertheless, we have some process to describe, but not classified, to describe this few classes of pseudo-Euclidean Lie algebra. Ober and Medina describe the Lorentzian, well, I think nilpotent Lorentzian pseudo-Euclidean Lie algebra, and most recent one include the work of Hisham Lebezioui. This one, a remarkable class of pseudo-Riemannian Lie groups, and the second one in pseudo-Euclidean Novikov algebra, and with Boussetta in journal of algebra here. Okay, but although the process of double extension are not considered as classification, but he gives some method for the construction and deconstruction of the algebra considered. But it is a very interesting process to understand the structure of pseudo-Euclidean flat pseudo-Euclidean Lie algebra. Okay, now in this recent work of Hisham Lebezioui, he considered a class C of flat pseudo-Euclidean Lie algebra such that the derived ideal GG is the left annulator, is the annulator of the Levi Civita product of this. This implies in particular that this Lie algebra are two solvable, okay? Because the bracket is defined by this one. The bracket is, you have the Levi Civita product. If you consider the commutator of the Levi Civita product, we find the bracket of Lie algebra, and if you have this This one is in the left annihilator. It's clear that you have x prime, y prime equal to 0. Okay. In this case, you have the Lie algebra, the underlying Lie algebra of this Levi Civita product is to solvable. He proved that every Lorentzian pseudo-Euclidean Lie algebra in this class C with the degenerate derivative ideal is obtained by double extension, by the flat double extension, in this case. Okay? Double extension for the double extension process of Medina and Aubert. Okay, all time with double extension by one-dimensional Lie algebra. It's also shown that if G is an element of C, such that G is nilpotent, then in this case, he proved that all time you have the derived ideal is degenerate, and in this case, he proved that we can, in the nilpotent case, we can obtain this Lie algebra by a sequence of flat double extension starting from Euclidean abelian Lie algebra. In the case where the derivative ideal is non-degenerate, he gave a characterization of the element of C for any signature. However, the flat double extension process of Aubert and Medina, used by Hisham Lebzioui, in the case where the derivative ideal is degenerate, is flat double extension by algebra of dimension 1. But this process does not provide an inductive description of all elements of C. It's the problem. Just because in the case when we have in the case Lorentzian, the problem is it's not easy, but we have all time one-dimensional ideal completely isotropic, such that its orthogonal is also two-sided ideal of Levi Civita product. In this presentation, I will show you how some of the show you some results here. And the aim of this study is to continue to study this class C, started by Lebzioui, and in particular to give an inductive description of all elements of C for any signature. For this purpose, we introduce a double extension process of pseudo-Euclidean symmetric Lie algebra, either by algebra of dimension 1 or by algebra of dimension 2. The case of resolution of this problem is to introduce a new double extension, not just by algebra, not all time by dimension 1, but another double extension by algebra of dimension 2. The double extension by algebra of dimension 1, in this case, is just double extension of Aubert and Medina. In the case of pseudo-Euclidean Lie algebra, left-symmetric algebra, I just let us remark that this one, right? Because it is very easy to verify that if you have pseudo-Euclidean flat Lie algebra in this condition C, is exactly left symmetric, left symmetric, and disons not flat, pardon, not symmetric but flat, and flat, it's equivalent to G, the vector space G with the Levi Civita product is left symmetric, and G, and this left symmetric algebra is L algebra. Okay, just donc it is donc if you have G is left symmetric, is flat Lie algebra, pseudo-Euclidean Lie algebra is equivalent to G point. This one is the Levi Civita product is left symmetric is left symmetric, and G point is L algebra, is equivalent. Okay, this one, that means that LX is the same. Huh? Is the same. Using this new double extension technique, we reduce the inductive description of the element of this C to those whose derivative ideal are non-degenerate. Okay, we start by if we consider pseudo-Euclidean flat Lie algebra, such that G endowed with Levi Civita product is left symmetric and L algebra, we show that if the derivative ideal is degenerate, we will show that we can construct this algebra by double extension by one dimensional algebra or by two dimensional algebra, and after some steps by this double extension, we found pseudo-Euclidean Lie algebra left symmetric, but the derivative ideal is non-degenerate. Huh? This I think it's clear here. Just the idea. I will give some detail after this introduction. Huh? Okay. Now, if we consider this type of pseudo-Euclidean Lie algebra A, where the derivative ideal is non-degenerate. Huh? What about this class? Huh? We have this condition. Huh? This condition here. Pseudo-Euclidean non-associative algebra is I recall the definition. Pseudo-Euclidean non-associative algebra is a non-associative algebra endowed with symmetric non-degenerate bilinear form, such that left multiplication by any element of A is skew-symmetric. And in the case of left symmetric algebra, this type of algebra is is pseudo-Euclidean if this left-symmetric algebra is endowed with non-degenerate bilinear form, such that the multiplication by any element of R is skew-symmetric with respect of R. Okay, that's the definition of our subject here. If you consider a non-associative algebra, then on the underlying vector space, we define the two following new binary operation, this one and this one, okay? Commutator and anti-commutator. We do not by A plus the algebra with this product, and A minus this one. The non-associative algebra is called admissible algebra if A minus is a Lie algebra. Okay. We do not by this one the derived ideal, and this one is just the vector space. The vector space generated by this type of product, x1, x times y. Okay. The first result here, just like lemma, if we consider a pseudo-Euclidean left-symmetric algebra, pseudo-Euclidean, the orthogonal of this one is exactly the element of R such that the right multiplication is 0, and the orthogonal of derived ideal of R minus is the set of element of R such that Rx is symmetric with respect to this product. The proof is very easy. It's just sample calculation. You can we can explain this the first assertion. If you have this one here, this one is if and only if you have this one, and in this case we have a pseudo-Euclidean non-associative algebra. We now, by this definition, we have this one now. All the time you have this, okay, minus z, and this is equivalent to this, and the second one is just some easy calculation to prove this. But it is very interesting to know the orthogonal of these two particular subvector space of R. Okay. Now we have this proposition or second lemma here, but it's very just this type of result is the technical result to found some isotopic ideal of this Lie algebra. Okay, of this Lie algebra, we have this. The first one we can prove just by sample calculation that this intersection here is contained in the orthogonal of the derived ideal of R minus. Consequently, this one is exactly completely isotropic to say the ideal. You can check that this derived ideal is two-sided ideal of this left-symmetric L algebra, and the orthogonal of R is an anti-commutative left ideal of this, and more in addition, you can check that you have this identity here. Okay, it's not very difficult. You have some calculation here. It's not just some linear algebra here. Now we'll show that the class of pseudo-Euclidean Novikov algebra is included in the class of flat pseudo-Euclidean left algebra. That means that this class of Novikov algebra is included in the class C, considered by Hicham El-Bzioui. Novikov algebra is contained in the class C. To prove this, we have this proposition. If you consider a left-symmetric algebra, then A is Novikov algebra if and only if the left multiplication by this product is there. Okay? It's very simple structure in this algebra. The proof is not difficult. It's just some calculation by the scalar product and the invariance the invariance by the multiplication, by left multiplication. You have this one, and this one. If we take this one here, you have -1, and here you use here you have this one. No, this one is the fact that Novikov or R algebra, and we make some calculation by adjoint, and we found that this one, this is exactly this one, and we conclude that you have Rx is 0, and in this case you have this, okay? Because we work in the Novikov on the Novikov algebra. You have this one. The converse is obviously true. As consequence, if you consider a Novikov algebra, then A is a pseudo-Euclidean left symmetric. If you consider a pseudo-Euclidean Novikov algebra, then this one is a pseudo-Euclidean left symmetric L algebra. Okay, it's very easy. By the last proposition, we have this. It follows that we have this. D'accord? Non, virgule ici. Come here. This one is L. Okay. A, and therefore A is a pseudo-Euclidean left L algebra. Okay. Then Novikov, the class of pseudo-Euclidean Novikov algebra is contained in the class of pseudo-Euclidean left symmetric L algebra, but pseudo left L algebra is exactly the class C. D'accord? It's like the class C. But not okay. But the Novikov class is strictly this one. Say that the class of Novikov pseudo-Euclidean Novikov algebra is contained strictly in the class of left symmetric L algebra. Is strictly contained. Why? We have this example. If you consider the four-dimensional vector space here, and the product of R is defined by this. You have D1 here, D1, D. Okay. You can by classical calculation, you can prove that this one is a pseudo-Euclidean metric of signature 2, and this Lie algebra is left symmetric algebra, and sometimes L algebra, but we have this, but it's not Novikov algebra, because we have this, we have D1, T2, O1, it's dot here, is this one, and T1, E1, T2 is 0, then R is not pseudo-Euclidean Novikov algebra. This example proves that the Novikov pseudo-Euclidean algebra is strictly contained in the class of pseudo-Euclidean left symmetric L algebra. Okay. In the following, I will recall the definition of minor algebra. It's a very important class. And in particular, this class appears in the study of Lie group with pseudo-Riemannian structure. The definition of bilinear algebra is a left symmetric algebra such that you have this decomposition. You have H is a non-degenerate subalgebra with nil product, and it's orthogonal with respect to this scalar product is a non-degenerate two-sided ideal of R with the nil product for any x in H. In addition, we ask to Rx to be skew-symmetric with respect to this one. Okay. This type of algebra is called minor. We call this type of algebra minor algebra. But here we recall also that minor Lie algebra here is just in general non-associative algebra. Non-associative algebra is minor algebra is left symmetric, and we have this. Okay, here Lie algebra is a pseudo-Euclidean Lie algebra with this decomposition. All time you have here commutative or abelian Lie algebra, and its orthogonal is an ideal, an abelian ideal, such that add x is skew-symmetric, but just for x for any x in the abelian Lie algebra. Okay. In this paper, John Minor proved that Euclidean flat real Lie algebra is a minor Lie algebra. So for this reason, we call this type of Lie algebra, or flat Lie algebra, minor Lie algebra. Okay. The first proposition, the first result in this for this class, if you consider a minor algebra is left symmetric algebra with this decomposition. I recall H is a subalgebra with nil products, and its orthogonal here is an ideal. B minor algebra, then Rx is 0 for all x in H, and Lx is 0 for Lx in orthogonal of H. Donc, Just by simple calculation, we can prove this. Now, if we consider a non-associative algebra and the symmetric non-degenerate bilinear form, in this way, then this one is minor algebra. Pardon. As non-associative, if and only if A minus is a minor algebra, and the product here, this one, is its Levi Civita product. And these two definitions are equivalent. If you work in Lie algebra, if flat Lie algebra, if you want to work in the non-associative algebra, you should consider the underlying vector space of the algebra with the Levi Civita product. If you want to work, if you have non-associative algebra or left-symmetric algebra or minor algebra, in this case, if you want to work in the category of Lie algebra, you should consider A minus. It's equivalent. Huh? And any minor algebra, this one is very interesting. Any minor algebra is a Novikov. Okay? Is a Novikov algebra. The proof is very easy, but this result is very interesting. All minor algebra is a pseudo-Euclidean Novikov algebra, and the proof is not it's not very difficult. Just some easy argument to prove this. Conversely, donc we have this one. Now, if you work in pseudo-Euclideanly left-symmetric algebra such that is non-degenerate with this non-degenerate, if your derived ideal of R minus is non-degenerate, in this case, you have this result. Rx is 0 if x is in this orthogonal. In particular, we have this. And in this case, this orthogonal is exactly this one. And consequently, we have this. In particular, we have this. You have a sample situation of this. If the derived ideal is non-degenerate, the product in R is very, very simple. Okay, you have this one. Okay, this one. The proof is not very difficult to. And corollary of this result. If your derived ideal is non-degenerate, in this case, this one is a minor algebra with H is exactly the orthogonal of derived ideal of R. And the next proposition, look, all left symmetric algebra when A is non-degenerate is all time a minor algebra. And the proposition here, you have equivalence between three classes. If you work in if you work in the left symmetric algebra with is not degenerate, then the following assertions are equivalent. A is L algebra, is equivalent to A is a Novikov algebra, is equivalent to left Leibniz. It's exactly the same. If you work in the left symmetric algebra such that you're non-degenerate. Okay. Donc for this, we can now just it's not very difficult. I just some simple idea to prove this. But here, if you want, if you have the right Leibniz, if and only if this one. Okay. According to this proposition, to this equivalence between these three classes, the three classes is equivalent to describing pseudo-Euclidean no-vector algebra is equivalent to describing pseudo-Euclidean left Leibniz algebra. To do this, we will use the process of double extension of Leibniz algebra introduced. We introduced the process of double extension in this paper. But here, using just a sample case of this double extension. I explain this. I explain what about this definition or this process of double extension in the case of left or in the case of left Leibniz algebra. But in our case, we have left Leibniz algebra, but also we have left-symmetric algebra. We have these two structures in the same time. And if we consider two endomorphisms of the vector space, and A0 is an element of R, KD, KE, two one-dimensional algebra, we consider this new vector space with this product, okay, with this new product here. We use this two endomorphism and the structure in R. You have this definition explicitly the product or product in this algebra. And in this case, we prove that this new vector space of dimension equal to dimension R plus 2 is the left symmetric and left Leibniz algebra if and only if we have some condition on D, delta, and A0, and this condition as here. Okay, we have this. Okay, we have this condition, and if this one is a left symmetric algebra, that means that this relation, this condition are satisfied. In this case, in this algebra, we can define this bilinear form. This bilinear form, we have a duality between D and E, and the vector space spanned by D and E is in the orthogonal of this one. In this case, we have a left symmetric and left Leibniz algebra, which called the double extension by a line, by one-dimensional, of the pseudo-Euclidean left symmetric and left Leibniz algebra by means this data, like this data with this condition. Okay. This condition, conversely, if you consider a pseudo-Euclidean left symmetric algebra which contain an element E with this condition, and the right and left multiplication is 0, we consider D here, and we can prove that this, if we have this condition, we have this element we can prove that this left symmetric and left linear can be obtained by double extension of left symmetric and left Leibniz algebra. That's like this, like this. Okay. I think it's the theorem. The last theorem in this part. Be observed left symmetric and left algebra, left symmetric algebra. Then A is either a minor algebra or A is a double extension by line of the pseudo-Euclidean left symmetric and left Leibniz algebra, and the proof is very easy. It's very easy. Donc, if you have this one, and we have by last proposition we have this one. Therefore, we have this. It's easy to check that the orthogonal is exactly 0. Consequently, this orthogonal is a subalgebra of R satisfying this. If R orthogonal is not degenerate, in this case, you have a minor algebra. If no, if R is degenerate, in this case, you can find an element here. This element verify this one, and thanks with this, thanks to for what we have called above, R is a double extension by line. The consequence of this result. Any pseudo-Euclidean left symmetric and left Leibniz algebra is either a minor algebra or can be obtained by a sequence of double extension from minor algebra. Note that this result on pseudo-algebra significantly improve those obtained by Hicham-Lebziri in this project. Here I give here in a sample description of this type in any signature, because in the paper of Hicham-Lebziri, he gave some result in the Lorentzian case. I think the time is over, no?
Yes.
But just if you
but
just
you may make at some seconds.
1 minute, not just
1 minute would be okay. Mm-hmm.
Wait, 1 minute. It's only that inductive description. Donc, in this description, we reduce the study of this type of pseudo-Euclidean left symmetric algebra to those to the minor algebra. But minor algebra is not. We don't in the Euclidean case is the classification in the classification by classified by minor. But in the case of non-degenerate defined non-definite case, in this case, the minor algebra, the structure is not clear. But we can describe this class by double extension of module. It's a new double extension, but I don't have time to explain this. But just in the case when we have a degenerate, in this case is very interesting. In this case, the key of the description is Lie theorem. But in this case, if you consider left and L algebra degenerate, this ideal, this set, this vector space, this sub-vector space is non-zero, but it is a two-sided ideal in this case. And you can consider this representation of the Lie algebra. This representation by the multiplication is given by this one, and this is the representation of R minus 1. And in this case, we know that A minus is two solvable algebra, and we have only theorem, and Lie theorem give us an ideal of dimension 1 or 2. If the dimension of F1, you have a double extension of Medina and Aubert, but new things here, if your ideal is two-dimensional, and in this case we introduce a new process of double extension by dimension 2, and we prove that all of this pseudo-Euclidean Lie algebra is obtained by these two-dimensional here. Just define in conclusion that you have this type of result. Generate, you have this theorem. This theorem and double extension of or by double extension by dimension 1. In this case, your this Lie algebra is dimension 1 and 2, or A is obtained by double extension by two-dimensional associative commutative algebra V. In this case, dimension of U is dimension A or cat. Okay, and just the final result. If you have A is non-degenerate, you can obtain all of this left-symmetric algebra by a sequence of double extension from a Novikov algebra, and Novikov algebra is described in the first part. Okay, and thank you very much. And sorry.
Yes. Thank you very much, Saïd, for your very nice talk, and in particular the final result was somehow remarkable. So, are there questions, please? Oh. So you are all well connected. You may perhaps unmute your micros. Are there? Yes. I mean, I of course I have question. My first, if I may, my first question would be the following: you were talking about algebras which are at the same time left symmetric and left Leibniz.
Yes.
And I mean, these are two strong conditions at the same time. I could imagine that one may, even if you only have these two conditions, that you can already say something yeah, can you somehow say something about this class of algebras, or is that really large? I mean,
no, this class of when you have in some time Novikov left symmetric and left Leibniz, and
yeah,
left case is equivalent to Novikov case. Okay.
Yeah.
It's equivalent. I consider this case. I consider because in the paper, in this paper, the paper of Hisham Beziri, in the Journal of Algebra, he didn't remark this equivalence. Okay, and in the paper in Journal of Algebra, the study I think, more complicated. Okay, and he considered just Lorentzian case, but Novikov, the case of Novikov algebra with pseudo-Euclidean flat, the Novikov algebra is flat. Huh? The structure is very easy. It's very simple. Huh? Okay, and I think is not very difficult to study this case. But this case is equivalent to this case. Huh? Okay, now.
Yeah, and if you impose these pseudo-Euclidean, I just wanted to know if you just don't talk about forms at all, but you just have these two structures at the same time, so left-symmetric plus left-Leibniz, whether this is already gives you strong conditions in the algebra. But I may be wrong. So you're
without pseudo-Euclidean. Okay, without pseudo-Euclidean.
Without. Just like this. Could you have? So is there a? Do you tell me? I mean, there is a large. This is a large world where
you have this
can't
one.
specify anything.
You have this one, no? Okay. Left symmetric is this one. Okay. This.
Exactly. Yeah. Mm-hmm.
And left Leibniz is no, not this one. Left Leibniz is this one. No?
Mm-hmm.
Okay. You have this one and this one.
Yeah, exactly.
Okay, exactly. And I think it's a very good question without pseudo-Euclidean, but I think it's very strong, no? Result. I don't know if this one, in the case of pseudo-Euclidean, we prove this. Huh? We prove that this one is in pseudo-Euclidean. Huh?
Yeah. Mm-hmm.
But now I don't know. We can study these classes without pseudo-Euclidean to have this. This okay, because if you have this one, no? This one is Lie admissible. Okay, Lie admissible.
Mm-hmm. Yes.
And the implies that this left symmetric algebra. This left Leibniz is also Lie admissible because
of course,
because
yeah.
And we know that if you have this, we have the in addition this if this one is Lie admissible, we have this one. Okay, if you have a left Leibniz Lie admissible, then we have this new identity. Huh? Okay, and I think we can prove something. Huh? But I don't know.
Okay. But this was just a question.
Very good question to have. But I think it's very strong to have this one and this one. Huh? Okay.
In
the case of pseudo-Euclidean, we must study the case when the derivative ideal is non-degenerate. Okay. And in this case, you have equivalence between left Leibniz and Novikov. It's the same. Huh? And in this case, we have the class is very easy. Just I think just three. This one is the. In this case, we have this one. But we must describe this by double extension. Okay. Some double extension, and this remark is not not exist in the paper of Hisham Ibn. Okay,
I see.
This remark is not exist, but with this remark, the result of Hisham Ibn is I think it's very easy to prove many things in this paper, and with this property we can we give the description, the inductive description of all Novikov pseudo-Euclidean algebra in any signature. Okay.
Mm-hmm.
But in the paper of Hisham, it's just in the case of
yeah, I remember PhD.
Okay. But I think without pseudo-Euclidean, I will see this. I will see this one. I think it's a very good question.
Okay. I just have another question. I mean, if you the motivation, of course, comes from differential geometry, right? Yes. So you have you look at Lie groups carrying, say, a left invariant, a flat Euclidean or pseudo-Euclidean metric, and
left invariant.
Left invariant, yeah. So not of course bi-invariant. This would be much simpler.
No, left invariant.
And so if you generalize, so you go a little bit, so you go from say Lie algebras to Lie Yamaguchi algebras, right?
Yes,
which describe these in the same situation would describe naturally reductive homogeneous spaces, right?
Yes.
And then of course, I mean, there's a technique to go to again to Lie algebras. And but of course, the role of the curvature and torsion is now different. Yeah. So
yes.
In the first case, your curvature considers whole vector space, and then in the second one, of course, the curvature. If you take this extended algebra, two ways, of course, then the curvature only concerns the subspace. Yeah. But anyway, perhaps one could do similar things and ask similar questions. But I don't know. So you are working with Busetta, Mohammed Busetta, and so I don't know whether he is present right now, but whether did he say anything to this, or how all this could generalize or should generalize to these?
The problem is very difficult. Okay. It's very difficult. In the case, if you work in general in homogeneous spaces, it's very difficult. If you consider the case of symmetric spaces, symmetric spaces is I think it's not very difficult to generalize this. In the case of symmetric, because we have some equivalence between symmetric spaces and the Z2-graded.
Yeah, of course. Yeah.
I think in this case we can prove something, but in general it's very difficult to.
I see. Okay. Mm-hmm.
Yeah.
Mm-hmm.
But it's very good question is comme d'habitude.
The third question. So if Abdel Nasser Makhlouf was there, he would perhaps ask the question whether he had done some classification of these structures in low dimension.
Oui. Yes. There is a few classification of this by Medina, I think not Medina, but by Busetta and Lebziwi, I think in dimension 6 or 5, I think. But because the description, the double extension is not classification, but it's a very interesting method to construct example, to classify, like in my talk, if you consider, attends, yeah. Non, c'est difficile. You have some example here, okay? Just example to say. No, example. You can just this example. Donc, if you consider a four-dimensional algebra, donc we can prove that this four-dimensional algebra with this product is just a double extension. Is
okay.
to 2 with this, and this one is 0. Okay. Like this, if you consider some Lie algebra, you can try to prove if this example is double or no double extension. Example one is very simple. Huh? If you consider the three-dimensional Heisenberg Lie algebra, you prove that this one is dimension 1, okay?
Mm-hmm.
And you make the double extension by one dimension. Okay? You have this one and this one, and you have this. The Heisenberg algebra, or three-dimensional algebra, is a pseudo-Euclidean L algebra. Okay? Is a pseudo-Euclidean with this. Okay? This one. This one you have a four-dimensional algebra, and not Novikov. This one is not Novikov, but this one, example is two-dimensional algebra with this one. All time, this one is you have this, and you can take the list the list of Lie algebra in dimension 4 or 5. But the difficulty is to classify pseudo-Euclidean.
I can imagine. Mm-hmm.
Okay. Mm-hmm. Classify, and you should introduce the equivalence of double extension, or classify by bracket this algebra. I think it's not in general. In general, I think Mohamed Boussetta, Hisham, and other people use some computer to make some classification. But I recently with Hisham and Bahu, with Bahu, we classified all nilpotent Lorentzian Lie algebra, okay? Without computer, okay? Without computer, and we give a classification, not description, but a classification all Lorentzian. Comment on dit, on a découvert. Hein? Donc, en fait, in this, I think the information for this type of problem, the referee of this the referee on this paper of classification of Lorentzian nilpotent algebra. They gave us interesting information. The double extension of Medina and Aubert is also a double extension by Margulis. In the case of in the domain, in the algebraic groups. Okay.
Okay.
We can consider if you have pseudo, if you have a flat, if you have a flat structure on Lie algebra, it's you can make, or you can consider the representation defined by Levi Civita product. Okay, in this case we can integrate this representation to groups, and now this integrate this to algebraic groups. But it's very difficult. I think there is comment on dit façon. Façon, c'est
ways. Two ways.
Two ways to study this problem by algebraic way or by geometrical ways. Okay. By geometry of algebraic groups. And in this case, it's very difficult to make a classification by just by bracket, or it's not. It's not very easy. Huh? But I think we can ask for the dimension of dimension 8. What about a classification of left pseudo-Euclidean left-symmetric algebra? Okay, yeah, but it's not. I think it's difficult because I prove here that all of this algebra is too solvable. Okay.
Okay, yeah, and that's already
too solvable. But the case of minor, in the case of definite, the Lie algebra is not nilpotent. It's too solvable. It's very difficult to. It is very difficult to classify solvable. Or, I think too solvable. Okay, but you can prove you can classify two solvable algebra, Lie algebra of dimension I think 7 or 8, and we can look for some pseudo-Euclidean, classified pseudo-Euclidean circle, and L algebra. No, it's a good program. But my first problem is to understand the structure of this Lie algebra. Okay. To understand by double extension, it's the first step to understand this structure, and for given dimension, allowed dimension, we can ask, but it's not very easy. Huh? Bon, it's my answer to your question.
Okay. Yeah, thank you very much. So again, are there any other questions, please?
Une minute. Hein? Attends. Une minute. Yes.
Yeah. Do I hear any other questions, or let me check the chat? No. Yeah, if this is not the case, let's thank the speaker for your very nice and interesting talks with deep results. And I don't know whether, as a chairman, I have the right to close the session, or if the organizers want to make some announcements, this would be the case. Otherwise, I would say we thank Saïd Benayadi for his nice talk. And
thank you very much for your attention.
And wait for the next seminar. So do the organizers want to say anything?
No, I think enough. We can finished here.
Yeah. Okay. So bye-bye, everybody. And the next seminar will be announced, or there's a plan somewhere on the internet, I suppose.